All right, welcome to this explainer. If you've ever felt completely bogged down by the sheer volume of AI jargon out there, well, consider this your roadmap. Today, we're taking a guided tour through the taxonomy of machine learning algorithms. We're talking about those absolutely essential methods that actually allow systems to uncover deep insights without having to be manually programmed for every single scenario.
Okay, let's just dive right into this. We're going to break this entire taxonomy down into 6 distinct buckets today. We'll start with the core of machine learning, move into feature prep and metrics, and then explore the main paradigms: supervised, unsupervised, reinforcement, and finally wrap up with deep and semi-supervised learning. So let's kick things off with section 1, the core of machine learning. At its core, machine learning is a massive shift. Basically, it moves us from giving a computer a super strict, rigid recipe to letting the computer invent the recipe itself. These systems analyze vast data sets to uncover latent structures, and they adapt to dynamic environments automatically. They literally bypass that old school, rigid, rule-based coding entirely. Now, you might be wondering, why does understanding this specific taxonomy matter? Well, it's the engine behind modern decision-making across almost every industry. It's exactly what allows healthcare systems to diagnose anomalies, finance platforms to flag fraud in literal milliseconds, and cybersecurity networks to predict the next breach before it even happens. Moving right along to section 2, feature prep and evaluation metrics. There's an old running joke that data scientists spend like 80% of their time here, and honestly, it's for good reason. You absolutely cannot throw garbage at an algorithm and expect gold. We have to meticulously engineer our features. That means scaling numbers, encoding categories, and creating interaction features to expose those hidden relationships. Doing all of this prep work right is what actually prevents overfitting and totally accelerates the training process. Now, what's really interesting about this slide is how we actually grade these models once they're built. Notice the stark dichotomy here in how we evaluate different tasks. If we're, say, classifying spam, we look at things like precision, recall, or F1 scores. But if we're trying to predict a continuous number, like next quarter's revenue, we switch over to regression metrics, calculating the actual magnitude of our errors through mean absolute error or our squared scores.
All right, section 3, supervised learning, predicting outcomes. As you probably already know, supervised learning is basically like a student studying with a master answer key. We train our models on perfectly labeled data, carefully mapping specific input features to known target outputs. The whole goal is so the model can eventually make highly precise predictions on entirely unseen data. So the crucial point here is that within this supervised realm, it really boils down to 2 main tasks. First, classification for sorting things into discrete categories, spam or not spam. And second, regression for mapping continuous numerical trajectories, like forecasting tomorrow's market temperatures. To tackle these, we kind of escalate our tools based on the complexity of the problem. You might start out with linear or logistic regression for simple trends. But when the data gets tangled up, you escalate to decision trees to get clear rule hierarchies, or maybe aggregate them into random forests to kill off any overfitting. And for those incredibly complex, high-dimensional spaces, like image categorization, support vector machines, or SVMs, become your real heavy lifters. Now, supervised learning is incredibly powerful, for sure, but it demands heavily, perfectly curated data. So what happens when your data doesn't have those predefined labels? What if you're just sitting on massive amounts of raw, messy information? That brings us to section 4, unsupervised learning, hidden patterns. Without those handy predefined labels, unsupervised learning is kind of like walking into a pitch black room and trying to feel out the natural groupings. We use a few different tools, think of them as different types of flashlights, to do this. K-Means clusters data by distance to a center point. Hierarchical clustering builds these nested family trees of data, and DB-scan groups by sheer density, which honestly makes it the ultimate tool for filtering out noise and detecting weird anomalies. And this brilliantly illustrates how unsupervised learning also tames overwhelming complexity through dimensionality reduction. Principal component analysis, PCA, compresses high-dimensional data so we can capture the maximum variance using the absolute fewest features. Meanwhile, t-SNE excels at nonlinear mapping. It essentially lets us visualize incredibly complex, multi-dimensional clusters right on a simple 2D or 3D graph. Let's shift gears to section 5, reinforcement learning, taking action. This is where algorithms learn by actually interacting with dynamic environments. Think about how AI learned to master chess or, navigate autonomous vehicles. It's this continuous loop. The agent perceives its current state, it takes an action, and the environment spits back either a reward or a penalty. Through sheer brute force trial and error, the agent continuously updates its policy to maximize its long-term score.
But here's the catch, the fundamental dilemma: exploration versus exploitation. Does the agent risk trying brand new actions to discover massive hidden rewards? Or does it just safely exploit the actions it already knows will yield a decent, favorable outcome? If you lean too far into exploration, learning basically crawls to a halt. But if you exploit too early, your algorithm gets permanently trapped in a totally mediocre strategy.
Finally, we hit Section 6, Deep and Semi-Supervised Learning. First up, semi-supervised learning. Look, manually labeling millions of data points is incredibly, prohibitively expensive, so this approach gives you the best of both worlds. It uses just a tiny fraction of labeled data as a guide, and then unleashes it on massive volumes of unlabeled data to extract those hidden patterns. It drastically boosts your predictive accuracy without completely bankrupting your data budget. Let's move to NC and see how this builds into deep learning architectures. These basically mimic the human brain and practically automate feature extraction entirely. We map the specific architecture to the data type. Convolutional neural networks, or CNNs, serve as our visual cortex for images and video. RNNs and LSTMs act as our memory for sequential and time series data. And transformer models? Well, they're completely rewriting the rules of advanced natural language processing. So there you have it. We've mapped the foundational trunk, the absolute crucial prep work, and the branching paths of supervised, unsupervised, reinforcement, and deep learning. You now have the complete mental taxonomy you need to build robust, intelligent systems. At this point, the real question isn't what these algorithms are capable of anymore. The question is, which impossible problem are you going to solve with them first?